I am Sadiq Biabanifard and I'm presenting this video as an attachment of manuscript, multistage OTA design, matrix description to circuit realization. With the scaling down of CMOS technology, feature size and fabrication advancement, demand for high gain amplifiers rises. Two possible solutions are cascode and cascade approaches. The cascode techniques increase DC gain by placing MOSFETs vertically and is not compatible with low power supply voltage since limits voltage swing significantly. So designer's tendency leads to multi-stage amplifiers. These amplifiers meet desirable DC gain easily, but due to increasing the number of stages, instability issues emerge. Consequently, frequency compensation of multi-stage amplifiers becomes an important and main part of design procedure. Since now numerous methods and techniques have been presented to frequency compensating multi-stage amplifiers, generally we can define frequency compensation as a network includes feedback and feedforward paths. These paths relocate poles and zeros to reach desirable frequency response. We can implement these paths by using circuit elements and blocks such as capacitors, resistors, buffers, and even differential blocks. On the other hand, the main part of amplifier, the stages, are descriptive independently, which is cascade combination of GM stages. This structure, independent of frequency compensation network, produces some terms in transfer function, which we call these terms as fixed terms. Any probable frequency compensation network can be added to the structure without affecting fixed terms. In return, frequency compensation network consists of different structure, depends on design style, can produce variable terms. In this work, we introduce three general compensation blocks to ordering compensation networks description. According to our knowledge, using these three blocks, almost all compensation network can be realized. In our proposed method, we inject the differential signal between first and third stage to the output stage via compensation capacitor. By increasing the frequency, this structure begins to improve frequency response since the compensation capacitor behavior and the phase difference between first and third stage are more significant at higher frequencies, so we expect to improve the frequency response. In order to obtain the transfer function of a multi-stage amplifier, we can rewrite node equations as shown. These equations contain constant and variable terms. Now solving these equations leads to obtaining symbolic circuit transfer function. In order to use symbolic transfer function, we can consider previous experience and knowledge to logical range of numerical values for symbolic variables, and exploiting a simple genetic algorithm, we can find the relative optimal values. This process can be effective significantly if we use an appropriate cost function for GA. As shown, we define a simple cost function using most important parameters. For circuit design in the form of transistor corresponding to the numerical values obtained in previous step, we use a diagram-based approach. In this way, the target parameters are GM and equivalent output resistor for each stage. So, according to illustration, bias voltage and MOSFET dimensions can be obtained. Now, given that the circuit design requires insight and knowledge at the transistor level, and that the exact transfer function of the circuit is very bulky, complicated and inefficient, the need for simplification is to be felt. To do this, we again use the GA and we propose the simplified transfer function with the appropriate precision. The simplified transfer function reveals circuit dynamics and pole zero locations symbolically. Finally, in order to evaluate accuracy and efficiency of proposed design, the results of symbolic calculations and proposed numerical values in MATLAB are compared with the result of circuit simulation using HSpice. So in general view, we propose a comprehensive design approach from configuration selection to circuit implementation, harvesting matrix and binary matrix description.